look at the idea of hypothesis testing. Essentially, the basis of hypothesis testing is that someone's making a claim, and we want to use statistics to see if their claim is accurate or not. So in order to do hypothesis testing, we're going to start with what our hypotheses are. H0 is your null hypothesis. And then the null hypothesis is the actual claim that we're actually going to test in our statistical testing. So when we do our statistical testing, we're going to assume that the null hypothesis is true. And the null hypothesis is always going to be of this form. Mu is equal to some value, or p is equal to some value, depending on if we're looking at a hypothesis for a mean or a proportion. For now, we're just going to restrict ourselves to the mu case. And what it's equal to is going to depend on the problem. The other hypothesis is the alternative hypothesis, denoted by HA. And it can take one of three forms: less than, greater than, or not equal to, and this also depends on the problem. And once again, you can change all those mu's to p's if you're dealing with proportions. And which one of these we use, like I said, really just depends on the problem and exactly what it is we're trying to test. So let's start by just looking at examples of setting up these hypotheses. A researcher claims that if expectant mothers use vitamin pills, the birth weight of the baby will increase. And we know the average birth is 8.6 pounds. So knowing the average birth gives us the null hypothesis since it's always of the same form. We have mu equal to 8.6. On the other hand, this researcher is claiming that the baby will increase, so we're claiming that the weight will go up. So the alternative hypothesis would be greater than 8.6, since we're assuming that the weight is getting bigger. The mean number of defective USB drives per 1,000 is 18, and an engineer believes that using robots for certain tasks will decrease this. Since we know the mean number is 18, that gives us our null hypothesis. We have that mu is equal to 18. For our alternative hypothesis, we are claiming that this will be decreasing, so it's getting smaller. Therefore, we would have mu less than 18. Let's look at one more example. A psychologist thinks that playing soft music during an exam will change the results. In the past, we know the mean score was 73, so that tells us our null hypothesis that it's equal to 73. We then need our alternative hypothesis. This psychologist thinks it will change the results, but they're not claiming whether it's going to go up or down. So this is when we use not equal to. We're not claiming that they're going to get bigger or smaller. We're just claiming that we don't think they'll be 73 anymore, so not equal to. Now that we've got our hypotheses done, let's look at the idea of testing. Essentially, like I said, we're always going to assume that the null hypothesis is true, and then we have to show that that's wrong. And we're going to essentially use a sample to kind of see how far away the sample is, and use that to see how strong our evidence is. So, the idea. We're going to assume H0 is true. We assume our null hypothesis is true. We're then going to get a sample and find the mean of the sample. We then want to find what is the probability that we randomly got this sample. Assuming that H0 is true and that is the true population mean, what is the probability that we just randomly got a sample with our sample mean? The smaller probability that we get, which we call the p-value, means that it was unlikely that we got this sample. If this is the case, if our probability is just too small, we assume we made an incorrect assumption, that is that H0 is false. So if our probability is small enough, then we assume that H0 is actually false in the first place. So how small can it be? So alpha is our significance level. And this is given to us in the problem, and it's essentially our cutoff point for our probability. We could claim HA is true even though it's not, and the chance that we actually do that is alpha. And we can also say that H0 is true even though it's not. And that is a more complicated error to calculate. However, we can say that if we try to reduce the chance of one of these, we increase the chance of the other. In reality, it's most common for alpha to be equal to 0.05, but it technically could be anything. So now that we have that done, we kind of have the basic idea of hypothesis testing, and we can slowly start looking at actually calculating these.